Hi all, so this is lecture 18 of MA 221 course, and today I'll talk about some more tests on uh, series. So remember, we know that this is like P series, summation 1 over n to the P, n varies from 1 to infinity, and this converges if my P is bigger than 1. And the series diverges if my p is less or equal to 1. We have already seen this. And we also know this is geometric series, right? Summation 8 times r to the n varies from 1 to infinity. And that series converges if modulus of r is less than 1 and diverges if modulus of r is bigger or equal to 1. Okay. Now the goal of this lecture is to compare given series to the series we already know. Okay, and most of the time those will be either P series or the geometric series. Okay, cool. Let me see let me solve some of the examples. So if this is my given example, summation n equal to 1 to infinity 1 over square root n to the n. I can compare this series with summation 1 over 2 to the n, right? And then the relationship between these two series will be this inequality, right? Because there I have square root of n, where n is natural number 1, 2, 3, and so on. And here I have only 1 over 2 to the n on the right hand side. So therefore, this quantity is obviously bigger. Okay, fine. So I know this identity. And now this right hand side is our known series. This is geometric series. Where my r is just half, which is less than 1. And this geometric series converges, right? Because modulus of r is just half, which is less than 1. So this converges. Okay, so we will see that we can infer the convergence of this series into convergence of that using comparison test. That will come later for it. And the second example is summation n equal to 1 to infinity 5n over n square plus 3 whole square. Okay, again I can write summation 5n over n square whole square n equal to 1 to infinity, and this is less than the given series, right? By the same logic, this 3 is missing here, right? So therefore this quantity is bigger than that quantity. This is bigger. Okay, but then this is nothing but 5 over n to the third summation n equal to 1 to infinity. And I can rewrite this as like this. And this is again converges, right? Why? Because this is P series with P being 3, which is bigger than 1. And remember, P series converges whenever my P is bigger than 1. In this case, P is 3, so this converges. Again, we'll see that the convergence of this right-hand side has something to do with the convergence of the left-hand side. Okay. Cool. Now, for the third example, I have square root n plus 1 over n. And now this is bigger than n square root n over n, summation n equal to 1 to infinity, right? Because now on the top I have n plus 1 and I just discard the plus 1. So therefore this is now smaller. Okay, this is like basic inequality. And this is summation n equal to 1 to infinity 1 over n to the half, right? Now this is diverges, right? This diverges because this is again P series with P being half, which is less than 1. Okay. The question is, can we again relate the divergence of right-hand side to the left-hand side somehow? Okay. The answer is yes. We can do that due to the direct comparison test. Okay, what does the comparison test states? It says that suppose summation n and summation bn are, I'm not writing n equal to 1 to infinity every time, are series with positive terms. Then the following two results hold. The first one is if summation bn converges and an is less or equal to bn for all n, then summation an also converges. And the second result is if summation bn diverges and an is bigger or equal to bn for all n, then summation an is divergent. Okay. And that's it. Do not take the converse of the statement. It does not hold. Okay. If so, this is like a one-way direction. The results is true for one way. Not the reverse way will not hold in most of the cases. There's a proof for this. I'll just very roughly sketch it. This is not needed though. Why this is this result hold? Because if you see for the result 1, if summation bn converges, then its partial sums are bounded. Right? Because that's the like if and only if condition for convergence of a series. Now, if also I have an less than equal to bn, say my partial sums sequence for the series summation an is say Sn, and for the series bn is say Tn. Okay. Now as bn converges, therefore Tn is obviously bounded, say bounded by m, right? And now as an is less or equal to bn, then my Sn will be less or equal to Tn, right? Because why? What is Sn? Sn is just a1 plus a2, the sum of first n terms. And what is Tn? Tn is b1 plus b2 plus so on, bn, right? Now each of these a1 is less or equal to b1, a2 is less or equal to b2. So therefore, if you take the sum, finite sum, then also the inequality holds, right? Okay. Okay. And now Sn, as an and bn are like positive terms series, then Sn is obviously increasing. and bounded, right, by M. So therefore convergent, right? I hope things are making sense. For the second part, kind of same logic holds, right? Let me just take one more page here. Okay. For the second part, say summation, if summation Bn diverges, then its partial sum tends to infinity, right? Because the partial sum, the sequence of partial sum is increasing because the terms are positive, so it's increasing. And so an increasing sequence is not converging. That means the sequence must be going to infinity, right? Okay, this is a subtle point, so try to think about it. Now, and also we know that an is bigger or equal to bn, then what happens? Sn is bigger or equal to tn, where Sn and Tn are like just as same as 1. And this Tn is going towards infinity. So therefore, and Tn tends to infinity. This implies simply Sn also tending to infinity, right? Because Tn is going to infinity and Sn is bigger than Tn. So therefore, my Sn should also go to infinity. And therefore, summation An also diverge. Okay. Cool. Now, examples. So for the first one, we want to apply the direct comparison test. So I can see that 1 over, so obviously these terms are like positive, okay? There's no confusion about that. You can check if you want. If you put in 1, 2, 3, 4, anything, then the terms will be positive. So we can apply the comparison test. Now, have to be careful. So this is less than 1 over 3n square, right? By the same logic. And now if I consider the series out of these terms, summation 1 over 3n square, then this series is convergent. Why? By P series test, as here P is what? P is 2, which is bigger than 1. Okay. So if you compare with the result 1 there, so I have this inequality, an is less or equal to bn, right? Here, this is my an, this is my bn, right? And an is less or equal to bn. I can write this as like this, less or equal to, no harm in that. And also I see that bn converges. So the right hand series, this series converges. So therefore, what I can say is summation 1 over 3n squared plus 5n goes from 1 to infinity also converge. Okay. Cool. For the second example, okay, I need one page there. Second example was summation n equal to 1 to infinity 1 over 3n minus 5. Okay. Now 1 over 3n minus 5 is bigger than 1 over 3n, right? It's easy to see why. And now I can write this for more convenience. And summation 1 over 3n diverges, right? Again, P series test. Here P is half, sorry, P is 1. Okay. And now if I compare with the result 2 there, so I have the opposite inequality here, right? And I see that the right hand series is diverging. So here again, this is my an, this is my bn, this is my bn, and summation bn diverges. So therefore I can say that summation n equal to 1 to infinity 1 over 3n minus 5 diverges. Okay, sweet. For the next set of examples, again we have to see if the series are convergent or divergent using a comparison test. So this time I have sine 1 over n. So remember, sine curve looks like this, right? This is y equal to sine x, and this may be like pi over 2, 0. So this is 1. Okay. Then as you increase n, so the main problem here is to deal with sine 1 over n. So when n is 1, this is like sine 1. When n is 2, this is sine half. So therefore, I am coming towards 0, sine 0, right? Okay, so that's the direction. So this may be the first point, second point, third point, and so on. I'm coming towards 0 as n grows. Okay, now sine 1 over n, okay, sine 1 over n over n to the n times square root n is less than 1 over n times square root n. Why? Because I know that sine 1, so this is the 1. So therefore, sine 1 over n will be always less than 1, right? Because all of the values of sine 1 over n will be like possible values in there. From here to here is the possible values. And obviously that is less than 1, right? So I can say this inequality holds. Okay. And this is nothing but 1 over n to the 3 over 2. And again, summation 1 over n to the 3 over 2 converges. P series being P to be 3 over 2, bigger than 1. Okay. So by limit comparison, so by direct comparison test, more space I need. Summation n equal to 1 to infinity sine 1 over n square root n converges. Cool. For the second example, again, I have cosine 1 over n, right? So now cosine goes like this, right? This is 1 over 2. So again, we are going like in this direction. Say this is 1. So this is like half. And so on. So therefore, cosine n will like grow like this. And this is the ceiling for cosine 1 over n. So cosine 1 over n this time is bigger than cosine 1 over n, right? Because cosine half will be bigger value. Cosine 1 over 3 over 1 over 3 will again be bigger than cosine 1, right? So cosine 1 is the lowest among all the possible values of cosine 1 over n, where n is like from 1 to infinity. So, so now in this case, this is nothing but 0.998 over n, and summation 0.998 over n diverges, right? Again, P series, P being 1. So therefore, again by direct comparison test, summation cosine 1 over n over n square root n diverges, and varies from 1 to infinity. Okay. Now, for this following two examples, we'll again try to use the comparison test and see what happens. Okay. Again, both of these terms in the series are positive terms. So we can at least try to use the comparison test. So now in the first example, so this is 1, this is 2. So for 1 over 3n square minus 5 is, isn't it the same problems? Yeah, this is the same problems, but yeah. So you might think like this: I can use this inequality instead of what we have done before. Okay, this is also true, right? But here summation 1 over 3n square converges, right? Again, this is p test, p being 2. And but so I have bigger or equal to this inequality there. So if I try to compare, I'm in second case, right? But the issue is that I need to have summation bn divergent, right? This be summation bn should be diverging, right? But here what I see is this series taking the right hand side terms is converging. So therefore, I cannot use the result 2. Okay. So what happens is the comparison test fails. Okay. So therefore, we have to use the previous way, not this way. Okay. For the second problem, again, I can try to use this inequality instead of what we have done before. But then again, summation 1 over 3n divergent, right? So, but according to the um, comparison test, this series having the right hand terms of the inequality should converge. So therefore, again, comparison test fails. Okay. The next thing that I want to discuss is the limit comparison test. Before we discussed the direct comparison test. This is another form of comparison test. So in this case, let summation an and bn be again series of positive terms. and let that C being the limit of the ratio an over bn. Okay. Then the following holds. If C is finite and positive, then both series converges or diverges together. Okay. If C is 0 and summation bn converges, then summation an converges. And number 3 is if C is infinity and summation bn diverges, then summation an also diverges. Okay. The proof of this is out of our scope right now, so I'll skip that. Rather, I'll solve some of the examples. Okay, so for the first example, so the limit comparison test is quite difficult to use, in my opinion, compared to the direct comparison test, because here you have to come up with a series on your own. So see, in the limit comparison test, there should be two different series, and then you have to take the ratio, limit at the ratio. Okay. But here I have only one series, which is summation n equal to 1 to infinity 1 over n plus square root n. Okay, that's it. So my an, if I choose that to be this, then I have to come up with bn. And in this case, I have to take that to be 1 over n. Why? Because you will see in a while. So limit, if I come, and then if I take the limit n tends to infinity of the ratio an over bn, that will be limit n tends to infinity 1 over n plus square root n over 1 over n, which is, in other words, limit n tends to infinity n over n plus square root n. Okay, then take n factored out from the bottom, then I'll have like this, and n goes away, and then I have limit n tends to infinity and 1 over 1 plus square root n, which is just 1 over 1 plus 0, which is 1. Okay, so here C is finite and positive. So I know that both the series AN and BN converges or diverges together. But what is Bn? Bn is summation 1 over n. So summation 1 over n plus square root n and summation 1 over n both converges or diverges together, right? But summation 1 over n diverges, right? Again, like P series P being 1, this implies summation 1 over n plus square root n diverges. Cool. For the second example, where we have 2n square minus n plus 7 over square root of n to the 7 minus 5, and going from 2 to infinity. There you have an to be 2n square minus n plus 7 over n to the 7 minus 5. And then again, you have to come up with bn. Okay, but before that, let us just try to rewrite this like this way. Then this is into the 7, 1 minus 5. So if I take my bn to be 2n square over square root of n to the 7, then this is nothing but 2n square over n to the 7 over 2, which is, if I do the calculation, this is just n to the 3 over 2. But then limit n tends to infinity, an over bn will be limit n tends to infinity 2 minus 1 over n plus 7 over n square, and then the n square there and here will go away and give me like just a second, and gives me 2 and then 1 minus 5 n to the 7 there. Maybe it should be in square root. Yeah. Okay. Now how I guess that my bn should be that? Because I can see that this n square should be going away to have like a finite limit. And also n to the 7 is coming there. So to cancel n to the square root of n to the 7, I need to have square root n to the 7 there. So you have to be very, very, smart choosing your bn. So this is nothing but 2 minus 0 plus 0 over 2, 1 minus 0, right? This is 2 over 2, which is 1. So again, by the result 1 of limit comparison test, I can say that summation an and summation bn converges or diverges together. And the advantage of choosing this bn is this is again a p series, right? So we know summation 2 over n to the 3 over 2 converges, right, by p series test, which implies our given series, which is summation 2n square minus n plus 7 over square root of n to the 7 minus 5, and going from 1 to infinity converges. Okay. For the third example, okay, which is quite big, okay, for this example, I have an, which is the term of my given series, log to the third n plus 7 times log n plus 7. Okay, but I'll take my bn to be 1 over n square root of log to the 3n. Okay, and if I take limit n tends to infinity an over bn, then what happens? Limit n tends to infinity. This will be this n and that n will go away. So I have 1 over square root of log to the 3n plus 7 times log n plus 7 over 1 over square root of log to the 3n. Then this is nothing but so square root of log to the 3n over square root of log to the 3n plus 7 times log n plus 7. Then again, this is 1 over 1 plus 7 over log to the 3n inside square root. And then just log n plus 7. How I get that? I just took the, okay, let me just create one more step. So I've taken that factored out, and then I basically cancel this one and this one. Okay. So this will be 1 over 1 plus 7 over log to the 3n square root times log n plus 7. Okay. And now if I need to carry out the limit and tends to infinity everywhere. And this will be 1 over square root of 1 plus 7 of 7 over infinity, so which is 0, times infinity plus 7. So this is sort of like 1 over infinity, which is 0. Okay. So now you can see that why I have choose the bn like that way. Because then I see that there is one extra n there, right? In the term an. I need to cancel that. So therefore I have taken that n there, and this log to the third will give me issues. Therefore I need to cancel that as well. So therefore I have chosen it like that way. Okay. So maybe you will not get bn directly. You have to try out different things. And then after some time, you should get what your perfect bn look like. Okay, so now again, if I go back to the result, if my c is 0 and summation bn converges, then summation an converges. That's it. So the question is summation bn converging or no? So summation bn, which is again summation 1 over n, this. So the question was, this is convergent or not? Okay. My claim is this converges. And for that, you need to use integral test. Some example can be a little dirty. You have to use other test to verify that your Bn is convergent or not. So then it will become like, I don't know, 2 to infinity, because here all the terms are, okay. I have taken 2 to infinity because for n equal to 1, this is like log to the third 1, which is 0. So this will be like infinity in the sum itself, which doesn't make sense. So therefore, you should take it from n equal to 2 to infinity. Okay. Then integral test will say that both of this converges or diverges together. And then you take u to be ln x. Then this will be like 1 over e to the 3 over 2 du. And you just calculate it to like conclude that summation bn is converging. So by q of limit comparison test, summation an converges. Okay. Cool. Okay, so far we have seen all the series as having positive terms. Um, we'll see how to deal with terms which are not always positive. For example, like -1 to the n. This is not a positive term series, right? Because the first term is like -1, second term +1, and then again -1 +1. So in this series we have some terms to be positive, some terms to be negative. How to deal with that? That will come next.